Okay, let's get started. So it's a great pleasure to have Tilman Esslinger here, who's been visiting Harvard for a month or so. That's never sounded like it's not what we want. But yeah, we will manage. Okay, yeah, all right. So I'm gonna turn it over to Tilman, who can tell you about wonderful cavity QED work, which really nicely fits into this meeting.
Thank you very much. It's a great pleasure to be here, and also a pleasure to give a talk in the US without chat lag. So it's nice to spend some time at Harvard there. I thank also the hosts. So what I will talk about is self-oscillating. Many bodies say it's driven by dissipative coupling to a cavity. We will come in a moment what that means and what the context is. But maybe very briefly, when we look into the future, we might, of course, wonder what will do in physics, what will that look like if we have quantum computers or quantum machines or similar. And that will surely change the way we do it. And I think we should also not only look what can we do for the quantum computer, but we should also look at what can the quantum computer or these machines do for us. So therefore, I have a wish list for the quantum computer, quantum machine. So what I want, and maybe some people share that, is the input is actually a many-body Hamiltonian and a many-body state. To put that into the machine. And from the machine, I want the evolution of that state. And now comes the question to the output. So I most likely it gives me surprising results that one discovers new phenomena. And then, I mean, giving microscopic understanding and ideally also generalization. And for the use case, well, there one has to keep up in mind that if we want to build devices that use quantum many-body physics, then somehow we need to have that state or the exotic physics. So really, it's not enough just to have it in some quantum computer theoretically, that's like a Papiertiger, but we really want to have the state. The undoubted quantum advantage is, of course, LIGO, where you have the speed state. So you really want to have that. This is, of course, all an argument in favor of analog quantum simulation. I really love it. Of course, this analog quantum simulation also is getting very complicated, and then we have really to do with all sorts of options. And I don't want to go through all these options, since it's a long-range workshop. I will focus here on long-range interactions, here on cavity-induced long-range interactions. There, of course, if you click further, there are more different ones. There can be different angles. There can be multi-mode. A lot of options you get. And then there is also a second way how that works. You can choose settings. So there might be the setting, basis of matter, excitations you might want to look at. And let's look at the non-equilibrium settings. And they are specifically at this exotic self-oscillation. And then if you read there, they always have to read the fine print. Requires option 04A. Well, that's cavity induced, we're happy, and it requires option 05B. That's controlled dissipation. Okay, sorry?
It's 6A. There it is.
Okay, yeah, that's the title. You know, it's better. Okay, and as you will see, the self-oscillations, to be very brief on it, it requires a system which has two soft modes. And these soft modes, we will see, they will couple to different quadratures of the cavity, but you have two soft modes, and those couple by dissipation. Only the dissipation couples them, and then you get this self-oscillation. Okay, and that's the first part of the talk will be mainly in this setting. There is a Einstein condensate in a cavity, and the blue detuned light, and it comes from 60 degrees. And actually the back reflecting beam is weaker than that one. And you can also get information here, which is fairly relevant here, this phase of the light coming out, and that's a phase relative to the pumping. And that's what the quantum simulator looks like, and any other quantum computer. And that's a closed system if you open it. And here I would, this first part is the impact team where Tobias Donner and I are co-teams. Okay, that was what we saw. And at one day, they can do well that they saw these funny steps when they changed the power of the pumping. And then these steps are phase steps, and they were in multiples of by half. And well, my first reaction was, it looks like as an AMO physicist, I can easily say it's like a small type of physics. Definitely worthwhile to further look at it. And one can run these quantum simulators, of course, overnight, and then you get phase diagrams. And in these phase diagrams, these steps, these are actually in this region where you have the phases changing. So in the region where you first might have thought, let's not look at it, something is happening, but not interested. I will come to what that looks like more closely. So this delta, that's where the dissipation comes in. The two soft modes is not yet so clear. Will come. I will very briefly remind you of DC in cavity. There are, of course, a lot of people working on it, and in particular also with multi-mode systems. So we look at just a single mode. And I think the easiest way to think about it, and I will come at the end of the talk to a very microscopic picture, but here I think it's enough just a more macroscopic picture, where the BEC is basically a superfluid refractive index, and you shine light on it, and then you, you first, it's like you're looking outside, so you can just shine the light through. However, what's happening if you increase the intensity, at some point you see that light comes out of the cavity, and that is the self-organization, which I will propose at some point. And the reason is, you see that this is a kind of a Bragg gradient from which the light is scattered, and so the superfluid refractive index comes up with a density wave, and from this density wave, the light is scattered into the cavity. And the system likes to do that because if there's light in the cavity, for rating we can lower its energy. And so it makes sense that it comes up with the energy of the density ripple. Okay, and here in this case, it's an even odd symmetry. It's either 6 on the even or outside. And you can get phase diagrams like this, no light coming out of the cavity. Lights. And now the difference, it sounds as if there's a small difference in the setup, but the outcome is rather surprising. In particular, it not only told us about many-body physics, it also told us how to build lattices, which we've been building for almost a quarter of a century. So Here it's a beam retroreflected has 60-degree angle, and it's blue detuned. And blue detuned, you might think, well, everything that I just had said it doesn't make sense for blue detuned, because there, if you have more light, additional light in the cavity, then you increase the energy of the particles instead of decrease. However, for blue detuned light, with respect to that, of course, the phase of the scattered light is just opposite. And then you can easily imagine what is happening. So imagine you have a big beam of blue light, and now you have a density pattern, like shown here, which scatters in the opposite direction. It's digging holes, and so the system can lower its energy. And of course, we have here in reality a standing wave, and then we thought, okay, as long as my DC is delocalized, as long as the standing wave is weak, the DC is delocalized over this little modulation, then this will actually work. But however, if we have too strong pump light, it should the atoms should be squeezed where there's no light, and it should be more difficult to self-organize. And that was our expectation. We did the experiment, and we were quite happy. We saw this phase, and you see here we increased the pump light, and then the phase is vanishing, or you have to go closer and closer to the cavity reference to increase the coupling. But then there was something that was always called that is funny background for some time. I don't know whether it was a few days or a few weeks. It was called funny background. And at some point we thought, what is that? It was not just on one day, it was always there. And then we checked what is actually the phase of the light coming out of the cavity. For here we expected, okay, it needs to be related, modulo 2 pi, modulo pi, that it is related to the pump phase. And then what we found is a phase shift of pi half between orange and green, but it would also be a stable phase. So it is a phase. And because one of these phases couples to one quadrature of the cavity field, and the other to the phase shifted to the other quadrature, which is phase shifted, as is illustrated there on the right-hand side. And it was actually quite nice collaboration with Nigel Cooper. And usually you see the theory. If you are, couldn't you look at this and something exotic comes at much low, maybe too low temperature or something? They were slightly different. They told us, well, is it possible that your back reflecting beam is not perfect? Say, yes, of course it's not perfectly back reflecting. And then we started to understand, and from there we understand that the additional phase, because as I showed you, on this early slide, if you just have a running wave, yes, you get this density pattern. And now you can imagine you have a standing wave, and the atoms are localized in the minima. If you add a running wave, then you can also self-organize that. So that was quite important for us to understand, and then we. Yeah.
Plus the second beam is independent beam, or
no, it's just not perfectly back reflected. It's just that the standing wave is not. The standing wave is not perfect. You have not perfect back reflection, but you can.
Would we see the setup picture? The picture of the beam. Yeah, okay.
So here you come with a stronger beam. That simply the mirror is not perfect. It has technical reasons. It's inside vacuum and not so easy to change, but it has a certain reflection. And then of course, part of this beam, this would form a perfect standing wave, And now you have an extra amount of laser light, which is also there, and that enables this additional phase.
What is between the 120-degree angle?
And that is breaking an asymmetry, which leads to the pumping in a directional pumping. It breaks the symmetry. Otherwise, you would have a symmetric going back and forth, so you cannot go around the singularity. Okay. And then you can calculate, of course, what is the geometry of the light fields in the cavity that you can calculate. And then you see these are the two geometries, and the center of inversion symmetry is actually different for the two. It's shifted. Okay, and now, of course, the most obvious is, well, you think, okay, I have two phases with two structures, so you have some type of structural phase transition. You go from one to the other, and the obvious question is what's happening when you do that. And then we looked at it, and the nice thing is, of course, in these experiments, you have the cavity field comes out, and that basically measures the strength of your density wave or the order parameter. So you go over this transition and you can follow this order parameter, and then you can see that it goes from one phase and it oscillates a bit and goes to the other phase. So we looked a bit into that. However, you can also, well, here it is in a regime where there's very little dissipation. But you can also, by tuning closer to the cavity resonance, somewhat changing your atomic detunings, you can go into a regime where the kappa starts to play a role energetically. And so here that is a coupling, and here we go with dissipation. And if we increase the dissipation, then you see this oscillation in the phase. And then we were looking at that more closely. And what you see there, then you can again scan at different parameter regimes. And then you see that the phase that is oscillating goes pi, and then a half. So it always goes from, say, 0 to 5.5 to 9.5 to 6.5 to 3.5. So it starts in one phase, it does this oscillation and ends up in the second phase. And then it was COVID time, so we had time to think, and we needed to think quite a bit. And well, also we plotted the data in different ways. So here again, it is so there you see that is now kind of seen from an optics point of view, your cavity field. So we start here with the bright point. It couples to one quadrature of the light field that's fixed here, and then it oscillates around, picking up a phase. So there must be some movement, and then it stops at that phase. So these are the typical pictures, and then one can also see what is actually happening while this is moving, and that is illustrated here. And these parameters are slightly such that it's a stronger focus on what is happening. So it's a bit weaker the real part. But maybe again, so you can see that you have this pumping. It has two sides, get to one side, and so forth. And you can then write down your light field in the following way. You have an interference pattern, a short lattice, which is stationary, for kind of a lambda half. And you have a second lattice with lambda spacing, which changes which has a position which depends on phi. So depending on what phi is, that is what we actually measure, this two lambda or this double space lattice moves over the short space lattice. And that reminds one, of course, of topological pumping. Remind you that to create a topological pump, you take a static lattice with lambda half spacing, in addition, a lambda spacing, and you move the lattice over it. Experimentally, this is often difficult because, well, you take a 532 and a 1064 laser, and then that causes problems because of the refractive index and the positioning of the two and so on. But anyway, that is the mechanism. And what is happening there, I mean, if you have this static lattice, you add this lattice, you split up into two mini bands. If the lowest mini bands is full, then you would have an insulator. Nevertheless, you pump it and it is moving. So you could think of 1 year states also. You put one year state, and in the topological pump, you need just to avoid that the tunneling is at the same time 0 as the side offset, and then you get this pumping process. And now we thought, okay, so if it is such a pumping process, then we should also see a displacement of our cloud, which is where the displacement goes with phi and not with some speed. And the geometry should be perpendicular to the pump. And that's exactly what we could measure. We could measure that it goes with phi, the displacement, and we could also, we have two cavities, so we could go into the other geometry with slightly different parameters because they have So this is well, in a way, a novel form of topological pump, because usually in a topological pump, the handle is turned from outside. Here, the handle is turned by dissipation. So it requires a dissipation. In a way, the dissipation, if one thinks a lot about it, then one might come to the conclusion that dissipation takes a big role like an electric field gradient, like a linear force that is pushing the atoms kind of like in this pumping scheme where you turn from outside the handle. And here it is the dissipation and effectively a light pressure force with the dissipation only along the cavity. So also one can wonder how fast is this process going. So you have two modes with broken symmetry in these two light field configurations. And those two modes are getting soft, and due to at this regime where you have this oscillation, the two frequencies coalesce due to the dissipation. So you have only one oscillation frequency, and then you have one mode which has gain, one which has damp, and then you have oscillation, and then you reach the next phase. One can now also wonder, okay, so what does it in frequency space? One can look at the frequency of that, and this is here time is measured, but also the pump increases in the intensity over time. So it starts oscillating and then it getting slower and gets into the other phase. You could now also wonder what's happening if I stop here. Just pump go into this middle regime, what's happening? And what's happening there, it kind of just oscillates on. And at some point, it does then our signal gets weaker. This kind of continuous oscillation, of course, but it makes one think of time crystals, continuous, the concept of continuous time crystals. In a way, of course, time crystals are a very theoretical construct. You just want to have a system which does not exchange, well, no net exchange of energy with outside, because otherwise we don't want to have dissipation. And in a way, I think this system, a nice aspect of that, in kind of trying to think about it, is you have an adiabatic evolution. There is a topological protection because you have your mini band gap. So all this is keeps the system to have minimal energy exchange, and also it's a superfluid and which prevents low energy excitation. However, of course, in our system we have cavity loss, but conceptually, for someone interested in quantum optics, you could argue, even though I need dissipation, but I could always count my photon that's coming out. Of course, the real cavities are more difficult. Not every photon that would, we would be up to zero, so we could always smash off the photon. But the reality is that's not the case. But nevertheless, conceptually, then one could kind of, the system could keep in both superpositions, and you have a Schrödinger test. I could imagine that comes out if one does a real quantum optics analysis, which we have not. One can also ask, are there other settings for such self-oscillating? And the truth is, I think we wouldn't have been able to figure everything out if we had not done a previous experiment. And in this previous experiment, okay, we pushed another button, and that was a spin mixture button. So we looked at the spin mixture in the cavity, and this is from the cavity team. This is the present team, where Panos Christodoulou is a leading postdoc, and Manuele Landini was back then the postdoc. It's now in his book, and Francesca. So there now it's 90 degrees, okay? And the light goes through 90 degrees. We produce condensate in the spin mixture of MF equal +1 and -1. And we also, another change, dramatic change, is that we are able to rotate our polarization, so that it can either and have a strong magnetic field. So there you can kind of tune your scalar and vectorial coupling. And without going too much into details, there are two possible solutions you get. One is a density wave, where kind of both spin up and spin down are on the same minimum. But if you are magnetic field, if you depend on the vectorial light field coupling, MAF +1 and -1 do not always experience the same coupling. And there is the other regime. If you, at some point, if you tilt your polarization, then you get an antiferromagnetic spin wave, classical antiferromagnetic spin wave. You can imagine here also that you see, if you have a vectorial coupling, you get a phase shift between the two scatterers. So they overall, this is again constructed interference into the cavity. And it couples again to the other quadrature of the cavity. So it's the total phase is shifted by 90 degrees with respect to the density. And one can make measurements, say, change the angle of the polarization, and then you see that you have a density wave, and then you have a spin wave if you tilt. So you get these two regimes, and then there's a critical regime where the system has to decide, and then you can look at this regime more closely. And what you see there, as you increase the tilting of the angle, I think it's 55 degrees, 67 or so degrees, and then you see light coming out of the cavity and an oscillation of the phase. So your phase is running through again. And here again you have a soft mode for the one phase, and you have a soft mode for the other phase. And kind of in a simple picture, it kind of oscillates between density wave, spin wave, density wave.
Yeah. How is the spin and the light coupled? Is it the polarization of the light, or is it some relative basis, or?
It is well. You couple you tune the scalar versus the vectorial light couple when you tune.
How is the
polarization?
How is the light field in the cavity different for the antiferromagnetic and the?
It's phase shifted. It's phase shifted by 90 degrees. And you have in the appearance, you have a pattern. You
don't have a polarization either.
You have a polarization pattern. Yeah. You have a polarization. Yeah. That's crucial. Your light field has a polarization pattern, like in the old days of laser cooling. In one case, the light field has a polarization pattern created by the vectorial light field coupling. In the other case, it is not, or it has its periods in the same way. And usually those modes would be perpendicular to each other, but it is the cavity dissipation that couples those two modes. And that's why only due to the dissipation you will have the oscillation between those two phases. Very similar as in the other one, where the topological pumping was driven by the dissipation. In that case, it was kind of the photon comes in and, well, in a very pictorial way, photon comes in, might decay out of the cavity, and that gives a net momentum transfer, which pushes a little bit the atoms, and that leads to a coupling of those two modes. And one can determine the phase diagram, your polarization angle, and then the tuning, and you have more of this phase if you have more dissipation. And you can also see there, you go to limit saturation. Okay, let me now very briefly come to, well, non-equilibrium state. I think it should go to quenches now, yeah. To quenches and a bit more microscopic picture, because sometimes when things are with cavity, it sounds so simple. Well, it sounds like a James Cummings model, and we should know it. And then one goes back and wonders what is actually going on. And so let's go to a very simple situation and take an MF equals 0 condensate and have a laser pulse for 65 microseconds. So just looking at what is its interaction. And what we see then is, so these are MF equals 0, and these are -1, and these are +1 atoms, and these are momentum space pictures, and we see a pair production. So one pair, each pair is in superposition of those two. A pair production as a function of number of atoms. So we increase the number of atoms, and non-linearly the coupling increase. You might remember Monica Schleier-Smith work on the flip-flop processes in different little tracks. So this is kind of, one could look at it as a momentum space with a C for that process. Yet the process is always the same process that actually drives your whole density when it looks your, but the spin helps one very much well to measure, and also it helps to understand. Okay, one can look at this process as in nonlinear photonics, you have this type of three processes which go with the intensity or with the atom number. And of course, there are other work like where you have this conditional spin mixing, so you have two emit into 0 and they scatter into a plus or minus 1 in tracks, and that's right purely through collisions. And in thermal atoms in cavity, there has been work on related things, and also there are these colliding and contexts. And so here, the way one can think of it, very microscopically in this process, a photon comes in, it drives this atom. Of course, in quantum mechanics, don't ask me which, okay? It drives this atom. And this atom is scattering virtually a photon into the cavity. So it into a standing wave, so it absorbs, it scatters, so it gets this momentum. And then it goes back and forth in the cavity, and another atom takes the photon and emits it into the pump, and gets a kick backwards. And that's why it's not so surprising that one can get pairs. So this here is now without spin, but to have the process strong, well, you take a DC or connection. And then, of course, the question is, as long as you don't lose a photon, it's really cool. When you lose a photon, then you get information on your standing wave pattern and so on. And for these measurements that we have, the theoretical estimates are 10 pairs per lost photon. So quite substantial in the parameters where we were. So what you want is you want strong beam, good cavity. And the strong beam you can do if you go kind of to the tune out wavelengths where you don't have an AC structure. And here what we do is we drive the following processes again with the spin mixture. So we start in the MF equal 0, they condensate, then you emit into the cavity MF equal 1, and then this photon is taken and brings another one in the minus. So then you have created a pair. And now you will say, but what about super radiance? The trick with the whole thing is that the cavity is QE. So your super radiant process is suppressed, and the other process is resonant. You have to make it resonant. So I need to speed up. You can. There's another process. Here's a picture where you can think in that term. You have those two atoms, and via the coupling, one will spin up, and the other one. And this is a bit to interpret our pictures. They are Stern-Gerlach separated, and then we can do a bit statistics on these pairs and what is the statistics of those pairs themselves. And we have against variant Zeeman splitting. If we have a small Zeeman splitting, then we get ticking up red correlated to kicking down blue, and vice versa. And you can also look at the pair statistics, the individual pairs, they can run both the statistics, and we can then correlate, in particular, if we have blue spin up, then we get red spin down. And we can also look at what's happening with dissipation. What we would like, but we have not yet, but you have to do your steps, is of course to see that they are 3CP, so we can pair correlate, but we cannot see the non-classical correlation at this point in time. But of course, one would like to think of, you can make a device, a useful device, an atom interferometer with SU11 with this process. And that doesn't only need freezing, but it also needs that it's a coherent process. So one can ask, what about the coherence of this process? And there we are much better shape. So we can see actually the coherent oscillation of this current scattering process. So, well, we will do further work on that. And I have to come to an end. And I thank you all very much. And I would also, in particular, thank all the teams that were did not talk about, but this is a long-range workshop, and I thank you again for the organizers to invite me to you for this.
Beautiful work. Quick question.
Thanks a lot for the great talk. You described it very nicely what happens to all the nonlinearity of the quantum field, but what is actually going on in the BC? So you only said like self-organization. Is there anything else? Or
You mean in this process?
Yes.
Yeah. Okay. Or if you let's take that one, that process. That's closer to. I think what's happening, you know, you have your BDC, and in the end, we adiabatically eliminate the light. So we have the fluctuations in position of the BDC. And now, when this process happens, there is we create a correlation in a spin pattern with this spin up and with spin down. Since we have not measured and since the photon in the cavity has an unclear phase, it's just a correlation that we have created. So we coupled our fluctuation to another by our Raman coupling to another pattern which has exactly the same amount of spin here as there. But it does not, I cannot, I look at it as a discussion with Lana, and I said that it's a wishy-washy pattern. I'm not always so happy with wishy-washy, which, since it's not, and if it was classical, I would have a spin wave. But since the phase should not be defined, it's as long as I haven't measured a photon, then it's wishy-washy in the sense of a quantum mechanical wishy-washy. That's my picture. There might be better pictures.
Okay, one more.
I'm wondering, there's some experiment without any ±1 and +1, which this matter wave super radiance by Wolfgang
Yes.
Now, for this experiment, does it really need the cavity, or can we do that without the cavity?
It is the loss of photons. That's once your photon is lost, then you get the information on the wishy-washiness. You can get a super radiant stimulation and so on, all that you get, but a coherent process where I have 10 pairs that I entangle, that is much more difficult in the free space case. Of course, I can always look at my cavity as mirroring my condensate, and then I have, it's like having a super long condensate, which is a bit the Wolfram's situation. But you get these fluctuations into density, the classical fluctuations you get also in similar. I think he had done some fluctuating beams. I think that basically scattered beam was fluctuating, which is not so surprising since he has fluctuations. That's how I look at it.
Okay, so the answer is works without the cavity, but it may be difficult.
It's probably much less coherent. I think the thing is, what I like about that is usually in cavities, the annoying thing is the losing the photon is okay if we can measure it. If you lose it out of the mirror, it's annoying. And here, in a way, we come in from the side, and then the photon is just created inside and goes out without this mirror. So the mirror loss is less pronounced. That's what I think at the moment about it. But
The process to show never happened without the cavity, right? The process to show here is.
yes, but I could still have take the cavity away. A photon comes in, and then it's very fast. It's a very eager photon. It goes out from another one without having seen the mirror. Exactly, and the length, and they are close to resonance. But of course, we are nanometers away, so to avoid spontaneous decay. And I think the one point that I forgot to say, the key point here, of course, is that this process is super fast. It's 50 microseconds. So if you want to build an interferometer compared to, well, the collisions, the collisions are the 3 orders of magnitude slower. So if I'm not too over-optimistic, this is really cool.
Okay, all right, thank you.